Good morning all, and today we will continue start in fact with eigenvalues and eigenvectors. So that's a very useful, very applied topic in linear algebra, but relatively easier than what we have already gone through various area in this linear algebra. So what are the eigenvalues and eigenvectors? So you consider matrix A, for instance, 3, minus 2, 1, and 0 as 2 by 2 matrix. And this vector minus 1, 1 from R2, and another vector 2, 1 from R2, and just make a product AU and see what happens. So when you do this AU, the result will be minus 5 and minus 1. Nothing to point out here. It's just a matrix vector multiplication with this particular vector, and we got some other vector as usual in R2. But when we do that product with V, something special will happen. So what do you get here? You get 4, 2, which is nothing but the 2 times of the vector itself. It was not the case with this U vector, but with the vector V, something is special. And what is special? That when you multiply this A with this vector V, you are getting the same vector with different magnitude, just double of the earlier one, 2 times the 2, 1. The vector is same, meaning that with the U, when you multiply with A, you are getting some other vector AU, which is usually happen every time. But this V was something special, because when you multiply A to this V, you have a vector with the same direction, but with a different magnitude. Correct? And in fact, we are looking for such vectors because these vectors are special vectors and they have a very special applications in various engineering and science. So these vectors are called actually eigenvectors. So the question is how to find that eigenvector for given A, how to find that number which is sitting in front of this vector itself. So all these issues we will discuss in this lecture. So the definition, if we go for the eigenvector or eigenvalues, so let A be any square matrix. It can be real, it can be from complex, the numbers in this matrix. A scalar lambda is called an eigenvalue of A, eigenvalue of A. If there exists a non-zero vector x, that is also important, non-zero vector x, such that Ax is equal to lambda x. Yeah, so what we are looking for? We are looking for this lambda, which in the earlier example it was 2, right? And we are looking for a non-zero vector x corresponding to this A, so that this identity happens that Ax, when you multiply A to this x, only lambda times x should come. So naturally they are very specific. This number lambda is very specific, and corresponding to this lambda, this x is also specific. So we are looking for a given matrix. What are the possibilities for x and lambdas? So this lambda is called eigenvalue of A, and x is called eigenvector corresponding to this lambda, corresponding to this eigenvalue of A. So the eigenvector x, the vector x, is an eigenvector associated with the eigenvalue lambda, because there might be several possibilities to have different lambdas, and then correspondingly the x will be different. So geometrically, which we have already realized, an eigenvector of a matrix A is a non-zero vector x in Rn such that the vectors x and Ax are parallel. Yeah, so they are in the same direction. The vector x and ax are in the same direction. So we are looking for those vectors from Rn if our matrix A is n cross n. The second interpretation, an eigenvector x is a non-trivial solution of the equation Ax is equal to lambda x. That is, an eigenvector x is a non-zero vector in the null space of A minus lambda I. So we are talking about this Ax is equal to lambda x equation, which is nothing but A minus lambda times Ix equal to 0. So we are looking for these non-trivial x. There will be a trivial solution always that x0, 0, 0, 0 will satisfy this equation. But we are looking for a non-zero vector x. So that means, in other words, we have written that a non-zero vector in the null space, because all the solution of this equation A minus lambda Ix equal to 0 will be the null space of A minus lambda I of this matrix A minus lambda I. And we are looking for a non-zero vector. So slowly we will understand, because we need to do some examples, and then we will realize. But the first question is that how to get this x and how to get the lambda. So is that clear from the definition point of view?
It is written that geometrically vectors x and ax will be parallel. Like, do we like, can they be anti-parallel also? I mean, can lambda be negative also?
Can lambda be? Yes, 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 of course. They will be just parallel, so they can be in the other direction. The magnitude will be different. I mean, may be different, can be different. And the only condition is that ax and lambda x will be just parallel to each other. Fine.
So means there would be no rotation of the vector, just the direction would be remaining same. That's it. Like in the same, along the same line. That's it. Is that the concept?
Please loud. I did not follow you.
Sir, I was saying if that the line along which the vector stays is going to remain the same even after applying A. Is that the concept?
After applying A, so AV should be in the same direction. It can be in the opposite also, but should be parallel to this. So if V is this, the AV should be whatever this, AV in this direction, whatever. Yeah,
So,
but
so
should be
in
parallel.
that direction, any vector would be an eigenvector, right?
Any vector will be eigenvector.
No, sir. In that direction, I mean, like in that all vectors in that direction will be stretched or squeezed by the some value, right? On the transformation.
So any vector which gives this AV parallel, that will be the eigenvector. That is true.
Yeah. So any vector on that line.
Yes. Any vector on this line which is parallel to this one.
Okay. So there will be like multiple eigenvalues, right?
Yes.
So, but from the null space of A minus lambda, can we get multiple values of lambda?
Yeah, we will see now how to get it. Yeah. See, eigenspace will have the vectors, right?
Yeah.
Not the eigenvalue.
Yeah.
So null space of this A minus lambda will have. So the question, basically the fundamental question is now how to find eigenvalues and eigenvectors. Yeah, we directly come to this point. The problem is we have two things. So we have a matrix, given matrix A, and we want to get lambda and we want to get x. And what relation they have? Ax is equal to lambda x, right? So we have one relation, and out of this we want to get x and we want to get lambda. Correct? So there are two unknowns corresponding to this A, lambda and x. So how to get these lambdas and x corresponding to A? So you consider this equation, this is the most fundamental definition, always Ax is equal to lambda x, right? We will start with this because that is the relation we have for eigenvector. So we have Ax is equal to lambda x, that means A minus lambda I is x equal to 0, right? This is the relation between eigenvalues, eigenvector and the matrix, that A minus lambda I x will be 0. So the question is now that we have two unknowns, lambda and x. We want to find lambda and we want to find x then. The only information that will help us now, that we already in our definition we said x will be a non-zero vector, right? X will be a non-trivial solution of this system of equation. So to have non-trivial solution, what should be the condition here on this matrix A minus lambda I?
The rank should be less than n.
Yes, in other words, in more simplified form,
determinant should be 0.
Determinant should be 0.
Yeah. Determinant should be
0.
0. Because if determinant is not 0, you will get only trivial solution, right?
Yes, sir.
If the determinant is not 0, you will have only trivial solution. So the determinant must be 0 to have some solution, some non-trivial solution of this equation A minus lambda is equal to x equal to 0. That means this is must here, that A minus lambda I must be 0. So we got one more equation, that determinant of A minus lambda I must be equal to 0. That means the determinant here, once you simplify for this determinant, when you evaluate this determinant, what you will get some kind of polynomial here in lambda. Yeah, in the example you will see. So if it is 2 by 2 matrix, you will get lambda square. If it's 3 by 3, you will get lambda cube and so on. So you will get such an equation here in lambda. And this equation is called characteristic equation of A. And we need to first solve these equations to get all possible lambdas which can make this determinant 0. Fine. So the roots of characteristic equation are called eigenvalues. So we already got eigenvalues out of this, right? We got eigenvalues from the characteristic equation, all eigenvalues, all possible lambdas which can make this determinant 0. And then corresponding to each lambda, we will solve this system of equation. Corresponding to each lambda, we will solve this A minus lambda I x equal to 0. So the eigenvectors of A can be determined by solving the homogeneous system of equations for each eigenvalue lambda. Is that clear? Is this slide clear to all of you?
So means first we are finding the lambda, then
yeah.
I get.
Yes. So first we will find the lambda out of this condition. Yeah. So we got lambdas, lambda 1, lambda 2, lambda 3, lambda so n. If it is n by n, you will get this nth order equation and you will get n roots. And then corresponding to each, you have to find x by solving the system of homogeneous linear equations. Okay, so we go with now some examples. Just another definition here. So the null space of A minus lambda I is called the eigenspace of A corresponding to eigenvalue lambda. That's just, one more term we use, the null space of A minus lambda I. This is called eigenspace. Yeah. So the eigenspace is nothing but all eigenvectors plus 0 vector, because 0 is not an eigenvector. 0 vector is not an eigenvector, but if we include that also in the set, then this, because ultimately this is just the solution space of system of homogeneous linear equations. So that will form a vector space, and that vector space is called eigenspace. So in the eigenspace, we have, it's not the collection of all eigenvectors, but little more. You have to also add the the 0 vector. So all eigenvectors plus 0 vector will form eigenspace. Clear?
Sir, this eigenspace is for a specific eigenvalue lambda or for all?
Yes, yes, corresponding to eigenvalue lambda. For different eigenvalue, you have a different eigenspace.
Okay, sir.
Yeah, because the system of equation will be different.
Yes, sir.
Each lambda. So corresponding to each eigenvalue, you have a set of eigenvectors or eigenspace. So a simple question: find the eigenvalues and eigenvectors of A, which is 2, 1, 4, -1. Right? Matrix is given, and we are asking what are the eigenvalues and corresponding eigenvectors. So first you need to write the characteristic equation. That is the first step. You need to write the characteristic equation A minus lambda I equal to 0. A minus lambda I equal to 0. That means you have 2 minus lambda 1, 4, 1 minus 1 minus lambda. This equal to 0, right? And out of this you will get this one. You have to simplify a bit. So you have 2 minus lambda into -1 minus lambda. You have -4 equal to 0. And that simplify this. I mean, you get the roots. So you have to factorize it and you will get the roots. So it will be lambda -3, lambda plus 2 equal to 0. That means there are two values. One is 3 and another one is -2. So there are two eigenvalues corresponding to this A 2, 1, 4, -1. And both the eigenvalues are distinct in this case. They may not be distinct. They may be same. They may be distinct, but they will be always, if it's a 2 by 2 matrix, naturally you will get 2 eigenvalues. If it's a 3 by 3, you will get 3 eigenvalues. If it is a 10 by 10, you will get 10 eigenvalues. So the eigenvector corresponding to lambda 1 equal to 3. Now you have to take each of them and then corresponding eigenvector. So lambda 1 equal to 3. So that means you have to solve A minus 3ix equal to 0. This system of equation you need to solve now. A minus 3x equal to 0. So A minus 3ix is equal to 0. And you will get, can you solve that? So let me just do help here. So A minus 3i. So A minus 3i means here you will get -1, 1, 4, and -1 minus 3. So you will have -4, right? And then you have x1, x2 and equal to 0. Yeah, this is your system of linear equations. Or augmented matrix will be -1, 1, 4, -4, and then 0, 0, which you can reduce it. So -1, 1, 0, and then here you will get 0, 0, 0. Correct? So you have one free parameter. So x2 you can choose anything alpha, and then x1 will be also alpha, because here the equation says both are equal. So your eigenvectors corresponding to lambda 1 is equal to 3 will be alpha times 1, 1. Correct? And alpha you can choose anything. You can choose 1, then 1, 1 is an eigenvector. If you choose 2, 2, 2 is an eigenvector. If you choose 10, then 10, 10 is an eigenvector corresponding to lambda.
I have a question.
Yeah.
So, in this characteristic equation, we are getting something like this, a polynomial equal to 0. So it may happen that the roots are complex. So in that case also.
Yeah. If even A is a real matrix, you can have complex roots. True.
Complex eigenvalues are also considered.
Yes, yes, yes. The roots of this characteristic equation are called eigenvalues. They may be complex, they may be real, they may be equal, they may be distinct, whatever.
Okay.
Sir, what is the significance of complex eigenvalues? I mean, you can't possibly plot them on a real vector.
You can't?
Like this is a real vector space that we are talking about, right? Over R. So we can't plot like complex values there.
No.
So,
what you will get once you have eigenvalues, we will see. Let's just wait for some time. There will be complex eigenvalues. There will be corresponding complex eigenvectors. So still your Ax is equal to lambda x will make sense. You have Ax is equal to lambda x, that will make sense. So here A minus, so there are 3 lectures, going to be 3 lectures, so all your questions will be cleared, right? So A minus 3i x is equal to 0. And x is, so you can write one of them. I mean, 1 is an eigenvector, 2 is an eigenvector, 10 is an eigenvector, whatever. It's any multiple of this is an eigenvector. So corresponding to lambda 1 is equal to 3, we have this eigenvector 1, 1, or any multiple of this. Yeah, any multiple of this.
And sir, what will be the corresponding eigenspace?
Yeah, that is the eigenspace. So alpha times 1, 1. So any, I mean, this is the generator. 1, 1 is the generator for that. That is the basis, right? So the basis of that eigenspace is 1, 1. And now anything you take here, this is the set. This is the eigenspace.
So this is the corresponding to lambda is equal to 3.
Yeah.
Okay, sir.
This is eigenvectors we are computing. Now lambda is equal to 3. So this is the eigenspace corresponding to lambda is equal to 3. Yeah. So any alpha from real number, so it will generate this 1, 1 will generate the whole eigenspace. Any doubt? What is the dimension of the eigenspace here?
Sir, 1.
1, sir.
Yeah.
One.
The dimension is 1 and the basis is 1, 1, or whatever. 1, you can also say basis is 2, 2. Anything. So only one element in the basis, and any other element can be generated out of that generator, that basis. Clear?
Yes, sir.
So now eigenvector corresponding to lambda 2 is equal to -2. That's the second one. Can you compute? What will be the eigenvector now?
Sir, -1/4 or 1.
You are getting -1/4 and 1. This one? Yeah. Fine. So 1 minus 4 or -1/4, 1. You can multiply by anything to this one.
Sir, could you explain how you got lambda minus 3 and lambda plus 2 again?
This one?
Yeah.
These lambdas?
Yes, sir.
That's it. Solving this equation, a minus lambda equal to 0. So what is a minus lambda? It's a 2 minus lambda, 1, 4, and -1 minus lambda, right? Equal to 0. So what is this here? You can now simplify this. So you have 2 minus lambda into -1 minus lambda minus 4 equal to 0, right? This determinant of this. So
Yes,
what is
sir.
that? -2. Then you have -2 lambda, and then you have minus plus lambda, and then you have plus lambda square. You have -4 equal to 0, right? So what is that equation? Lambda square minus lambda, and this is -6, right? So once you factorize this, you have lambda -3 and lambda plus 2 equal to 0. Correct? And this implies lambda is 3 and lambda is -2. These are the two roots. Is that clear?
Yes, sir.
Okay, so you can get now that you can write down the characteristic equation. You have to solve that characteristic equation to get the eigenvalues. Once, see, the process will remain the same. So that's what I said. It is very easy. You don't need to remember much. I mean, anything. Only a minus lambda. Yeah. So a minus lambda equal to 0. You solve it. Get the eigenvalues corresponding to each. You need to solve the system of linear equations. You need to solve the system of linear equations, which I believe all of you are comfortable with. Clear?
Yes, sir.
It's a simple question. Do it.
Sir,
Find the
excuse me, sir.
eigenvalues. Yeah.
Sir, what if the matrix A given is not a square matrix? We
Yeah,
cannot
we
define
cannot.
eigenvalue in that.
Yeah, we will not get for non-square.
Okay, sir. And sir, another doubt I have is that the eigenvector that I get when we compute here is always of the form of a column matrix. I mean, can the eigenvector be of the form of 2 into 2 matrix or something like that?
No, no, no. That's a Rn. It will be from Rn only. You have
Yes, sir. It
you
will
have
be
Ax is equal to lambda x, right? So if A
yes, sir.
is n cross n, what should be x? It's n cross 1. It's n cross 1. So it's always Rn. So x is from Rn. If A is from n cross n.
Okay,
Nothing
sir.
else. Yeah. So
So
this
can
is
we
N cross M also X can be, because we only have to match N and N on both sides.
yeah, but eigenvector is not a matrix. Yeah. This eigenvector is a matrix. It's a vector from Rn.
Okay, sir.
Fine. So solve this. Find the eigenvalues and eigenvectors of A equal to 1, 1, 0.
Eigenvalues are 1,
What?
1, sir, 1.
Okay.
So I'm getting 0 and 2.
Yeah. So what are the
yes, sir,
eigenvalues?
0 and 2.
1.
1. 1 and
Yes, sir,
1.
1.
Just say
Yes.
1
1
and
and
1. Right?
1 and 1. Yes.
Yeah. So eigenvalues will be 1 and 1. Repeated eigenvalues. This is called repeated eigenvalues. 1 and 1. Now find the eigenvector. So now you have basically 1, right? I mean, for eigenvectors, you have only one eigenvalue, right? Because the two are same.
Sir, can you please check? I am getting 1 minus lambda square. Oh, sir, that was 0. I forgot
Yeah,
that.
got it?
Yes, sir. Made a mistake.
Also remember, just a result, it's a standard result. Once you have triangular kind of matrix, yeah, it's a triangular. All
Upper
zeros here.
triangle.
So the entries, the diagonal entries will be the eigenvalues. Whatever matrix, if you have even very big matrix, and if it is a triangular matrix, so here everything 0, it's a triangular matrix. So all these entries will be the eigenvalues. Fine?
Yes, sir.
Because the determinant is going to be just the multiple of those entries, right? Once you have A minus lambda I. So you will get those roots of the characteristic equation. So here the eigenvalues are these 1 and 1. Compute eigenvector corresponding to 1.
So 1, 0 is the eigenvector.
1, 0.
1, 0.
1, 0.
1, 0. So eigenvector corresponding to 1. Let me just see. So you have A minus I x equal to 0. That's the equation which will get you eigenvector. And then 1, 0 is the eigenvector, right?
Yes, sir.
Because you have A minus I means 0, 1, 0, 0, right? This is going to be your augmented matrix. Correct?
Sir, I have one doubt.
Yeah.
Instead of this, can we write 2, 0 as also an eigenvector?
Yes, 2, 0 is an eigenvector. 5, 0 you can write. You can write 100, 0.
Okay. All these vectors are corresponding to this eigenvalue.
Yeah. All these are eigenvectors corresponding to 1.
Thanks.
Fine? All?
Yes, sir.
Hello, sir.
Yeah.
So from these two examples, we saw that for one eigenvalue, there are many eigenvectors. This is the case for all?
Yes. Because you are solving that system of linear equations which has infinitely many solutions, always. Because you are looking for non-trivial solution. So whenever you have non-trivial solutions means you have infinitely many solutions. In system of linear equation, either you have unique, and when you have homogeneous, then always the trivial solution always exists. So there is no question of no solution. So for system of homogeneous linear equations, you have only two possibilities. One is trivial solution, another one infinitely many solutions. So you will always get infinitely many solutions. So corresponding to any eigenvalue, you will get, of course, infinitely many eigenvectors.
Excuse me, sir.
The only question is, which we will learn in a minute, how many are linearly independent? Yeah. I mean, whatever you write here, 2, 0, 5, 0, these are linearly dependent on this. So the generator is one only here. Correct? Though there are many you can generate, but one is important. All other are just a linear combination. Yeah, ask. You had some question.
Sir, eigenvalue of A and A transports will be same or different?
Yes, so we'll get those properties. Yeah, just wait. Fine. It's clear so far?
Yes, sir.
Okay,
Yes.
so we can move to the next problem. Just another very simple small results which we will not in fact prove in detail, but there is a very well-known theorem here in linear algebra that is called Cayley-Hamilton theorem, which says every square matrix satisfies its own characteristic equation. That's a very good result. Every square matrix satisfies its own characteristic equation. What does that mean? So you have a characteristic equation, determinant A minus lambda I equal to 0. Correct? That means you have this characteristic equation. Correct? And your A will satisfy the characteristic equation. So you replace here lambda by A. So that is a result. Fine. Which trivially you can somehow realize from here also, though formal proof is a bit lengthy. You have the determinant of A minus basically lambda you are replacing again by A. So A minus A 0 and then 0. So, but this is quite useful result that every square matrix satisfy its own characteristic equation. So you have a characteristic equation, you can replace that lambda by A also, and then some useful results you can get out of it. For instance, this one. Let A be 11 minus 6i, 4i, 1. Verify Cayley-Hamilton theorem for A. Just to see in this example. What is the characteristic polynomial? So this minus lambda, and you just simplify this, you will get lambda square minus 12 lambda and minus 13 equal to 0. By Cayley-Hamilton theorem, it should satisfy that A square minus 12 lambda minus 13 must be equal to 0. You can compute now A square. You can compute 12A. You can compute 13I. So once you compute that, you can verify, later after the lecture is over. So you have A square minus 12A minus 13I, and then you will realize that yes, this all cancel out, and then you have only 0, 0, 0 matrix. So A square minus 12A minus 13 will be a 0 matrix. 13I. That is the Cayley-Hamilton theorem. There are some applications of Cayley-Hamilton theorem. At least one we will see here. That use Cayley-Hamilton theorem to find A inverse when A is this. Just an example, but you can have many more to find this A inverse. You write down the characteristic equation of A. Again, A minus lambda equal to 0. That is the characteristic equation. Lambda square minus 7 lambda minus 2 equal to 0. The Cayley-Hamilton theorem says that A square minus 7i minus 2i must be equal to 0. This is a 0 matrix, right? 0, 0, 0, 0. Now, out of this structure, we can compute actually A inverse, because we know this relation here that this must be equal to 0. If you write down, you take a common here, A minus 7i equal to 2i, the 2i right hand side you can bring, multiply by this A inverse. So here you have A inverse, then A inverse here is A is gone, and you divide by 2. So what you will get, 1 by 2 of A minus 7i. So by this simple calculation, you got A inverse. So A minus 7i you can compute. A is given minus 7i and then divide by 2. So this is the inverse. This is the inverse. Provided that inverse exists. Don't try to get A inverse of those where inverse does not exist. Yeah. So if inverse exists, you can easily get out of this, equation.
Finding an inverse with Clay-Hamilton theorem, is it applicable for only 2 cross 2 matrix?
No. You can get 3 by 3 also.
Okay.
Yeah, anything. Because see, you have a relation. This is not, Kelly-Hamilton does not say that it satisfies only for 2 by 2. Any n cross n. So you will get such an equation, and there you have to see that you need to multiply some A inverse, so that at one side you get A inverse, at the side you get everything in terms of A, and then just you have simple multiplications of matrices and so on, plus minus, and you can get the inverse.
Excuse me, sir. Sir, Cayley-Hamilton theorem can use only for a square matrix.
Yes, for a square matrix. We are learning everything for a square. The eigenvalues, eigenvectors, that is characteristic equation, that is for a square matrix. Yeah, the statement also written there, right? I have written that statement. Every square matrix satisfies its own characteristic equation.
So, excuse me, sir.
Huh.
So, lambda is a scalar belonging to R, whereas A is a matrix. So, can we replace a scalar and a matrix anytime?
Not anytime. This is a
So only in this
special.
case.
This is a special result.
Okay. Okay.
That every square matrix satisfies its own characteristic equation. That is the very special result. Not like every lambda you can replace wherever it is by A. Yeah.
Okay.
So clear.
So, but for higher order matrices, it will be hard, isn't it? We will have to cube the matrix. We will have to square the matrix.
Yeah, true. If you have a higher order matrix, of course, to get such calculation of A inverse, you need to do, multiplications. You need to have A square, you need to have A cube, or depending on the order. Fine.
Yes, sir.
So find eigenvalues and eigenvectors of A 2 square root 2 square root 2 1. The applications, we will not be covering many of eigenvalues, eigenvectors, but I am sure in many of your other lectures, you will, maybe in second year or third year, you will come across with eigenvalues, eigenvectors for sure. So here you learn from mathematical point of view, but there are lots of applications of eigenvalues, and actually they tell a lot about the matrix. In fact, yes, we will learn some applications. Now we will move to the numerical analysis in next week, and there you will see that how useful are these eigenvalues and eigenvectors, indeed eigenvalues. So it tells a lot about the matrix and lot properties for in the numerical analysis. So in analysis, these eigenvalues are very much required. So you will see some really good applications in numerical analysis soon. So find eigenvalues and eigenvectors of A.
Sir, 0, 3 eigenvalue.
0,
Yes, 0, 3.
So
Yes,
the
sir.
eigenvalue characteristic equation A minus lambda I equal to 0. Then you get this determinant. So you have to just subtract from the diagonal entries. That's all. So 2 minus lambda, 1 minus lambda, simplify this. You have lambda, lambda minus 3 after simplification. So the lambda 0 and 3. You also got 0 and 3?
Yes, sir.
Okay, so 0 and 3. Now corresponding to 0, eigenvector
1 minus root 2.
1 minus
Minus.
root 2. Yeah, that's true. So
Yes.
1 and minus root 2. Clear this one? All of you got this eigenvector corresponding to lambda 1 equal to 0. If you have any problem, calculation question you didn't understand, you please ask. But don't skip. This is a very simple
Excuse me, sir.
chapter in terms of the calculation and all. Yeah.
Sir, is there any property like sum of root of lambda will be trace of the matrix?
Yeah.
Yes,
And
yes.
product of lambda equals to determinant.
Yes.
Yes. There are many. So some properties will go through, but these two properties are there. Yes. Yeah. So we'll go through many other properties soon. So now I am just getting that you should be comfortable with the calculation in the first part. Is it clear?
Yes, sir.
Okay. Now the other one, lambda equal to 3.
Root 2 1.
So you will get
2 1.
1. Yeah. So here the eigenvectors are minus 1, square root 2, square root 2, and 1.
So it's on the same line as the column vector, sir.
It is?
It is same vector as column vector of the original matrix.
Yeah. True. This happens.
No, sir. In for second column, it is not. For first column, it is.
Yeah, the first
correct.
only matches. Yeah, the first only matches. The second one.
So
No,
for
sir,
me, the first
original
one does
matrix.
not match.
Original matrix. Okay, okay. Yeah, maybe this is by chance. So this is not something, even original also you have minus 1 2 na, so there you have no minus sign.
Yes.
See, you have slightly different. Yeah, so these are the eigenvectors. So note that again a very important point which I will mention later on, will prove in fact that these eigenvectors are linearly independent. Yeah, if you check this and this, these are linearly independent, isn't it? And this is
Yes,
not
sir.
happening here. This is happening everywhere. When you have two different eigenvalues and you are computing the eigenvectors, those eigenvectors are linearly independent. Fine. Just an observation here. Later on, we will have a formal proof on this.
So the I. So, okay, I got my point.
Okay, no problem. So find eigenvalues and eigenvectors. Just practice again one more problem here itself.
So yes, I found my problem. Sir, it was quite obvious that eigenvectors would be linearly independent because they were being obtained from the null space, and whatever non-pivot columns we used to get from there, we used to get the linearly independent vectors only in the null space.
Yeah, but see, we are talking about two different null spaces now. Yeah, corresponding to two different eigenvalues. True.
Oh yes.
So then it's not that trivial to just say.
Yes.
So find eigenvalues and eigenvectors of this matrix. 3 minus 2 0 minus 2 3 0 0 0 5.
Their eigenvalues are 5 3 and 3.
Okay. So you don't need to write characteristic equation, and the eigenvalues 155, right?
Yes, sir. 155.
You got something else, right? 135.
Yes, sir. Yes, sir.
Yes,
One
sir.
155. Yes, sir.
155. Yeah. 155. Now corresponding to one eigenvector.
110.
Very good. So corresponding to 1, you have 110. Simple linear of equation, right? A minus lambda x equal to 0. So therefore I'm going fast here. So I don't have to do much. I don't have to, make you understand or process. I don't have to explain anything. A minus lambda I x equal to 0. You will solve, you will get alpha times 110, right? Now corresponding to that 5. Yeah, corresponding to 5.
-1 1 0 0 0 1. 2 are there.
Yes, sir. Two vectors.
So get, you got, this is the solution, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Same.
Yeah, because you will get this 0 row. Once you have -2, 0, you have here again 0, 0, 0, 0. So here also 0, 0, 0, 0. So there is only one pivot.
Yes, sir. Two
Two
free
are
values.
free. So x3 is free and x2 is free and x3 is also free.
Yes, sir.
So then you get this alpha 1 minus 1 1 0, alpha 2 0 0 1, right? So this is something more interesting, that you had this one eigenvalue 5 which was repeated, and then you got two linearly independent eigenvectors, right? So corresponding to 5, you have two linearly independent eigenvectors. -1 1 0, this is 1, or any multiple of this, or 0 0 1. Now you have two linearly independent vectors corresponding to lambda is equal to 5. Whereas there was another problem earlier where there was a repeated root, right? 1 1. I remember there was a problem where we had a repeated root. How many eigenvectors we got there?
Sir,
Only one.
Only one. So it is not like because 5 was repeated 2 times, therefore we got 2. This is not the rule. 5 may be repeated 3 times, still you may get only 1. So we will clarify this. For example, you have, so here find a basis for the eigenspace of A. You have this big matrix. What are the eigenvalues?
2.
Sir, 2.
2, 2, 2, 2. Yeah. So 4 times repeated. The eigenvalues will be 2, 2, 2, 2. As I said, it's a triangular matrix and the eigenvalues will be sitting in the diagonal.
Yes.
Clear? So you have 2, 2, 2, 2. Now you find out the eigenvector.
So 1, 0, 0, 0 means 1, 0, 0.
Only one, right?
Yes, yes, sir.
1, 0, 0, 0. So you have eigenvalue which is repeated 4 times, 2, 2, 2, 2. And you get only one linearly independent eigenvector. True. So the basis for the eigenspace is 1, 0, 0, 0 vector. This is the basis for eigenspace. Clear?
Yes, sir.
Just quick question again. Find the eigenvalues and eigenvectors of this just to practice. 1, 1, minus 2, 3. What are the eigenvalues?
Five and minus 1.
5 and minus
5 and minus 1.
5 minus 5.
I'm getting something else.
Yes,
Yes,
5
sir.
and
Complex numbers.
2 plus minus iota. Yes, sir.
So
yes,
how
sir.
you got the different values this time? Okay. So 2 plus minus I. You will get the complex roots of this equation.
So corresponding to 2 plus I, we will
Yeah.
get 1 minus I, 2.
Yes. So corresponding to this lambda 1, you get 1, 1 plus I. This is what you got, right?
Yes, sir.
Very good. So corresponding to lambda 1, which is 2 plus I, you are getting the eigenvector 1 and 1 plus I.
So this we can also write as 1 minus I and 1 also.
Yes, you multiply by some number. So for 2 minus I,
1 plus I comma 1.
1, 1 minus I am getting, yeah?
Yes, sir. 1 plus I comma 1.
Yes.
Same.
Yes. So if A is a real matrix, has complex eigenvalues, then the conjugate is also, that also you should note down, that conjugate will be also eigenvalue.
Can you please once repeat the last part, because I was actually not able to connect to Teams properly. Something
So there
happened.
is nothing much. It's just an example we have taken here. This was the example 1, 1 minus 2, 3 with real entries. You got two eigenvalues, 2 plus minus I. So same calculations what we are doing. There's nothing new here. So lambda 1, 2 plus I, corresponding to this, you got the eigenvector as 1 and 1 plus I. Yeah, that is corresponding to 2 plus I you will get. And similarly, corresponding to 2 minus I, you can compute it's 1 and 1 minus I. Yeah. The only thing you should note down that they will be conjugate, because you are getting that root of that polynomial equation. So definitely you will get the eigenvalue as in complex conjugate form.
So
And
means the previous eigenvector, if we take the conjugate of the previous eigenvector,
yes,
we'll get the new the other
yes,
eigenvector.
yes, the same relation will hold there also, that if Ax is equal to lambda x, then Ax bar is equal to lambda bar x bar.
Means finding only one eigenvector in this case would be enough.
Correct. So if lambda is the eigenvalue complex, its conjugate will be the another eigenvalue, and if corresponding eigenvector is x, then x bar is the corresponding eigenvector of lambda bar. That relation will hold.
Okay, sir. Got it.
The conclusion here is that you should remember this relation Ax is equal to lambda x, and these pair lambda and x are called eigenvalues and eigenvectors. Cayley-Hamilton theorem, that every square matrix satisfies its own characteristic equation. And eigenvectors corresponding to distinct eigenvalues. This is the observation, not a formal proof. They are linearly independent. We have observed. A real matrix may have complex eigenvalue, and both the eigenvalues and eigenvectors occur as complex conjugate pairs. I think this is what we have learned so far. Yeah.
So can you show previous page that is real property? Sir, here you have written conjugate of matrix A is A itself, I think.
Because A is real.
But A have complex entries.
No, A has a real matrix.
Okay, okay.
Sir, I think you have written wrong in case of second eigenvalue. Sir, there will be x2 equals to iota minus 1. And you have written 1 minus iota.
This one?
Yes, sir.
What
iota
was
minus 1.
What was
iota
the
minus
first
1.
eigenvalue? It was 1, 1 plus I. So 1
yes, sir,
minus I. This will be an eigenvalue.
Yes, sir. In the above, sir, matrix, you have written minus 1 plus iota 1 comma, sorry,
Okay.
1 0 0. So there will be iota minus 1, and I have calculated it is coming iota minus 1. Sir.
This one, this one?
Yes, sir. Yes, sir.
Okay, this is 1 minus I, no?
No, sir, this is iota minus 1. But in other steps, that x2 equals to 1 minus iota, there will be iota minus 1.
Okay, okay. Yeah, you check it. Maybe some mistakes are there. I'll check it. Yeah. Fine. So this is what we have learned, how to find the eigenvalues, mainly how to find the eigenvectors we know now. For a given matrix, we can compute eigenvalues, we can compute its eigenvectors. So in the next portion, next part, we will learn some properties of eigenvalues and eigenvectors. So maybe I have a small quiz for you guys, where based on just the computation of eigenvalues and eigenvectors, which you can just practice.